Hi, Civ 332 teaching team. This is Group 6's Stage 2 and 3 presentation for the Civ 332 course project. So we're going to start with Stage 2, question 3.3. In this question, we examine how road accident impacts traffic on the Queen Elizabeth Way Highway. So let's look at what happens when the accident occurs, reducing the flow of traffic on the QEW from 3 lanes to 1 lane. Before the accident, we can see that traffic is flowing freely along this stretch of highway. Then when the accident occurs, we can see a backwards propagating shockwave starting from the congestion represented by these red rectangles where the incident occurred with speed WAC as the queue builds up behind the bottleneck. At 32 minutes when the accident is cleared, this turns into a forward propagating shockwave with speed WAC moving away from the site of the incident. Now let's take a closer look at the interactions between flow and delay over time before, during, and after the incident. The blue line here shows flow without the accident, which stays relatively constant over the time of the simulation at around 5,000 to 5,500 VPH. The green line shows flow impacted by the accident. As you can see, at 12 minutes after the start of the simulation, flow suddenly drops right over here, with a constant decrease for around 20 minutes until the accident is finally cleared at 12:31, and flow then returns to normal levels. Now, we can take a look at a similar graph of delay time versus time. Again, the blue line shows delay time without the accident, which stays relatively constant over the simulation. Looking at the green line, we can say that delay time begins increasing right when the accident occurs, or at around 12:11, and it peaks at 12:31 just before the accident is cleared. It then decreases quickly over the next 10 minutes from 12:31 to 12:41 before reaching pre-accident levels. Now we can look at how the accident on the QEW affects flow on neighboring roads. In this case, the service road. For our blue no accident line, flow stays very constant over the simulation time, with small spikes and dips following the timing of traffic signals. On the green line, we can see that starting at the time of the accident, around 12:11, there's a small gradual increase in flow as more vehicles use the road to avoid the accident. And then around the time that the accident is cleared, flow starts decreasing as congestion builds up on the road due to increased demand. Finally, we can look at the delay time of the same neighboring road. For around 10 minutes after the time of the accident, delay time doesn't show any signs of increasing or decreasing, as commuters are still taking time to switch to alternative routes and the road has not yet reached its full density. Then, from 12:31 to 12:51, delay time starts increasing dramatically as traffic density increases, approaching jam density, and max delay is reached around 12:47 before slowly decreasing again as vehicles start switching back to the highway.
Okay, let's now answer stage 3, question 1.3. So for this question, we'll be designing a Webster controller for the Fowler and Leanne and Aramil intersection. And this method will essentially help us optimize the traffic signal timings for this portion of the road of network. And so we'll be using these values over here and also these values on the corner to help us with the design. So our first step is to select the signal phase. We'll be having 4 phases in total, as can be seen in this diagram. And we will then obtain our peak hour values for each phase, as can be seen on these charts, highlighted in yellow. We'll then convert our peak hour volumes into DHV, PCE, and LT volumes, but since we have no trucks and our PHF and our left turn factors are equals to 1, they will all remain the same value, as can be seen on this chart. We'll then calculate the yellow time to eliminate the dilemma zone, and that can be done using this equation over here. And we'll have to do this for both Fowler and Leanne and Aaron Mills. And as we can see, after plugging all these values for each respectful roads, we'll be getting 5.17 seconds for Fowler and Leanne and 5.57 for Aaron Mills. We can then calculate total lost time. So we have 4 phases in total, and our lost time for phase is 3.5 seconds. So that will give us an L of 14 seconds because our R is 0. We'll then optimize our cycle length. So we already have L, and we can find capital YI, which is also known as the critical movement, using this table over here. And once we do that, we'll be getting a cycle length of 75.14 seconds. We'll then calculate total effective green, And that can be done by subtracting the cycle length by our total lost time, which we get 61.14 seconds. And we'll then calculate our effective green time per phase within this equation over here. And once again, we have all the numbers, so we can just plug it in and we'll be getting these numbers. This is for our model. And similarly, we can then find the actual green time per phase using this equation. And once we do that, we get these numbers. Once again, this is our model. We then have to check pedestrian movements. So we know that pedestrian walking speed is 1 meter per second. So the time that it takes to cross fallen land will be 19 seconds, and to cross areas will be 29 seconds. Once we get those values, we have to check phase 2 and phase 4 and making adjustments if necessary. And once we do that check, we can then do a quick summary table here, round everything up so we have good, nice, even numbers. And we can then generate a phase plan summary diagram, which was done here. And once we have this, we can now input these values onto Aimsun, and we are done.
For this part of the presentation, we're going to discuss the design steps of installing ramp controls for 2 congested roadway sections on the network. The first being upstream at the on-ramp onto the QEW at South Service Road, and the second being downstream at the on-ramp onto the QEW at Mississauga Road. The first design step is to install the ramp meters at the entrance of the on-ramps, which is going to represent a traffic light at the location of the green box. The algorithm used for this ramp is Alinea, which requires a detector that measures downstream traffic. Here, it's placed where the ramp traffic merges onto the freeway, which you can see here represented by a blue box. The second design step is to set the parameters of the ramp meters. For demonstration purposes, an example was used for the upstream meter detector pair to showcase this design step. The control type was changed to a fixed type. The on-ramp flow was measured at around 1,000 vehicles per hour, and the flow at the upstream section ranged from 200 to 1,500 vehicles per hour. The last condition that's required for the ramp meter is the occupancy. This value will need to be set at the optimal value that will result in the largest flow downstream of the ramp. Since this value is initially unknown, we will start with an initial guess of 0% and iterate over multiple values to find the optimum. After completing the initial iteration with a value of 0%, the simulation was repeated in increments of 20% up until reaching a maximum value of 100%. After all of these simulations are completed, the results of all 6 experiments are plotted against flow and occupancy. From this graph, we're able to identify the occupancy values corresponding to the maximum flow, which is around 31% for South Service Road on-ramp and 28% for the Mississauga Road on-ramp, as seen from the graphs.
Thank you so much, Nada. And now let's move to the step number 4, where we plot the fundamental diagram, flow versus density graphs for merging area sections before and after adding the control values. As you could see from these graphs, red dots here represent the control values, which basically means the values after adding the ramp meter, while the blue dots here represent the before control values, which basically means the values before adding the ramp meter. As looking at this graph, we could see that density and flow here follows a normal green shield model, which is described by the parabola kind of shape, while in this for this location this pattern is not that visible, but in both cases we could see that the flow shifted from the lower capacity condition to kind of higher capacity condition by looking at this shift between the areas. And this pattern here is less visible again, but we still could see that the flow became more stable and the density of the flow decreased after adding the ramp meters. Now let's move to the step number 5. In this step, we plot output flows from the bottleneck sections before and after getting the control values. And the main pattern that we could see from the both locations is that before adding the ramp meters, our values were more consistent but also very clustered, while after adding the ramp meter there was more sharp drops and kinda the flow became less unstable, which could signalizes that on the initial stages ramp meters does help, but then the flow moves towards the congested side. Thank you so much.